So we finished up, I think we talked about, did we talk about VMs and containers? That takes like 2 seconds, so it's not a big deal.
I don't think so. Or
Okay.
unless I missed the last one.
Very important though.
Yeah, I think we talked about kernels, or maybe we'll just start here. So I've talked about operating systems and hardware a lot. Just a note that the smallest, most primitive part of software to an operating system is called the kernel. And the kernel is used for like CPU scheduling, getting the system time, starting a process on the CPU. It's very like around like the core components. And so you'll hear things about the Linux kernel, the Windows kernel, like that's just saying like it is basically the skeletal system of the operating system. And you can use functions to like find the time and things like that. Okay, VMs and containers, real quick. Operating systems run on hardware. There are also these things called virtual machines and containers. Virtual machines virtualize the hardware and the operating system on top of the operating system. So it's like a full virtual computer on the operating system. That includes like RAM, hard drive space, like CPU resources. Is actually pretty wild. You can decide how much of the real CPU you want to dedicate to being the CPU for the virtual machine. VirtualBox and VMware are great tools to build up to install a virtual machine. This is older technology. People use this to kind of like be able to hand one virtual machine to someone else, and then developers could like develop on a virtual machine that had all the dependencies installed, rather than like it works on my machine and doesn't work on your machine. But people don't use it typically as much these days. They all use Docker and containerization technologies. There's other containerization technologies like Singularity and some other ones out there, but most people end up using Docker. Docker is kind of like a virtual machine, except it's extremely lightweight and headless, meaning it doesn't have a GUI. It doesn't have like a lot of the other components. Basically what it is you can think of it as a virtual machine that uses as small of resources as possible while managing all the dependencies of the software that you would need within that operating system. So most of the time, the containers are Linux. And so you might have like an Ubuntu container. And that Ubuntu container runs on a piece of software that's on the regular machine, which we call a host machine, like the physical machine. And it's called Docker runtime. It's basically the runtime environment, the scheduler, if you will, for like the containers. So you can have a bunch of containers working together. Those containers can communicate to each other if you open up like specialized ports to allow them to communicate through Docker runtime, essentially. But it's functionally going from one container to another container as if it's going from one machine to another machine. And it's really useful for developers. We could talk more about this later, but it uses part of the system resources. It doesn't have a GUI. It's way less of a footprint than a virtual machine, and it's really easy. And we love them because I can hand you a Docker container, and it will, as long as you have Docker runtime and you spin it up, it will literally have all the dependencies that you need already included. So if it worked on your machine or my machine, it will work on your machine. That's what's great about Docker and why we use it. Any questions here? We can show an example of Docker later in software lessons. Okay, programming paradigms. We're finally here. Let's talk about it. So what are programming paradigms? So like this is going to get deep into like language and philosophy very quickly, but I'll keep it very high level. Like when you were learning like how to write English, for instance, you learned about like imperative phrases and like other types of like phrases. Like imperatives typically have like an exclamation point or period. Questions have like, a question mark, etc. Well, what we did was we took those semantics and we applied them to programming languages early on. And so we have these different paradigms, these different ways of writing software or using software. There's the command paradigm, which is essentially just you say what you want to happen and the computer does everything under the hood. So when you're using the terminal, for instance, if you ever open the terminal, a command. So if I type in help, for instance, that's not a command in this terminal, list. List, ls stands for list, and it's just a command. I want you to list stuff, and then under the hood, it's got all this other software that, boom, lists different things. So that's command paradigm, and we'll talk a little bit more in detail about it. Well, first off, there's the one for Linux, Windows, like everything has a terminal or a command prompt, and you've probably come across it before or heard people using it. It's like the basic way to navigate the computer with text, like I just did. You can change directories. Like if I want to go into the desktop, I'm now in the desktop. It says Ron Picard is the user at Ron Picard, MacBook Air desktop. Then I can go list, and this is all the files on the desktop, which is test.py, which we'll use in a little bit. So that's what the command prompt is, and command languages. So we have other, like command prompt is just one example. If you command software to do something and then it does it, that's command paradigm. Then there's procedural paradigms, which is more normal programming. Procedural, functional, and object-oriented typically build on top of each other, and even aspect-oriented, although this is rare to be used. Procedural programming is step-by-step instructions. Every command has to have procedural underneath the hood. You just don't see it from a user perspective. From your perspective, it's command. But procedural is where you tell the computer, I want you to do X, then I want you to do A, then I want you to do B. So you are designing what needs to happen from the bottom up. Examples of that are A equals 1. So I take a variable and I say that variable is going to be assigned, or we call it defined, as 1. There are ways to declare a variable without defining it, but you can't use it until you define it. So declare just means I state A is a variable. When I assign A the value of 1 through this expression, we call that defined. So A is now defined as 1. B is defined as 2. So now that I have defined my two, numbers, or my two variables, I can now define a symbolic expression to say like C equals A plus B. And then I can print C and I will get 3 because A is assigned 1 and B is assigned 2. And print is a function. We'll talk about that a little bit. That just prints to the screen, and I get 3. So it literally, when the program executes, it goes line by line. It says A is equal to 1, got it, stored in memory. B is equal to 2, got it, stored in memory. C is equal to A plus B, got it, stored in memory. Print C, and it goes, oh, I got to print C. What is C? C is A plus B. What is A plus B? A is 1, B is 2. So C is 3, and then it prints 3. Any questions on that?
Okay.
And speak up if you do, because I can't see your screen. Cool. Sweet. Pretty simple. So it gets more complicated from here. It just gets into types, and we might talk about types a little bit later at another lesson in more detail, but there are a bunch of primitive types. Basically, the processor has to know what the variable is, what type the variable is. And primitive types that are common are integers, floating points, which are basically big decimal numbers, 16-bit decimal numbers, doubles, which are 32-bit decimal numbers, meaning 32 binaries. Any number that can be expressed with that is a double. Characters are single letters, ASCII letters, and strings are multiple letters. So these are the typical primitives that you'll see in procedural programming. Procedural programming also has operators. So it's got arithmetic operators, and it's got what's called comparative operators. Arithmetic operators are your typical plus, minus, times, divide. And this gets really deep into binary theory, into binary operator theory. This is based on like semantics that we've created for like our typical numerical system. I can send you some articles that I wrote that are like formal methods, like from beginning to end as fast as possible. And it starts kind of with binary operations, and we can talk more about that. But for typical computer science, we have, plus, minus, multiply, divide. Multiply and divide end up in the processor as pluses and minuses. You can also do things that are like exponentials. Some programming languages support that, but again, those get turned into, multiplies, which get turned into pluses and minuses in the actual processor, because all you have is switches going on and off. So that's arithmetic operators. There's one more that I want to talk about. It's called the modulo operator, and it's very important to computer science. And it basically says that if I have 10 mod, which is the operator, 5, what is the remainder after the division of of those two numbers? So 10 divided by 5 is 2, and the remainder after the remainder digit after the decimal is 0. Now, if I were to say, 11 mod 5, I would get 2, and then I would get 1 over 1 over 5. And so the remainder after division is 1. I know that's really confusing. And I might even check that in math, but it's all about the first number after the decimal point, or like the remainder after the division is the modulo operator. We'll talk about why that's useful in an example maybe later, not today, but with FizzBuzz. We won't have time to get to that today. All right, comparative operators. These are also important. So you have ones that like add stuff together. You have ones that compare two different things. Comparative operators always result in either true or false. True is equal to 1, false is equal to 0. And so that's how the binary numbers represent them in the processor. So comparative operators are greater than, less than, equal to, greater than or equal to, less than or equal to. There's some other ones, but we won't talk about them. A equals 1 equals is a comparative operator. So it's just, in programming languages, you have to separate what is a comparative operator from what is an assignment operator. So an assignment operator is 1 equals. A comparative operator is actually 2 equals in programming languages. And we'll talk about that. I know I didn't represent that here very well. We'll show an example of that in a second. C is equal to A is greater than B. So what would C be? C would be true or false, depending on if A is greater than or less than B. You can print C and it'll print false in this case, because A is 1, B is 2, A is less than B. So this expression therefore evaluates to false, and it prints false. Then there's the last set, which are logical operators. Logical operators are not, or, and. And basically, they're similar to compare. They're kind of similar to the veins to comparative, but slightly different. So not means it is something is not true. So what I would do is, if I had this comparative operator, A equals B, but if I said C equals not A is greater than B, because A is greater than B evaluates to false, and I said not, then I want not false, which is true. So C would then return true. This takes a lot of left brain thinking, and is often really hard for brand new kind of computer scientists to get their heads around for a while. There's these things called truth tables that really help kind of plan all this out. We might talk about it in a later lesson, but it's more of like a foundational computer science thing. So not is like the reverse of true. So whatever the expression evaluates to, it just flips it. Or is basically a statement that says, if I say A is equal to true and B is equal to false, and I say A or B, or if A or B means that one of those has to be true. If one of those is true, then the whole expression is true, if A or B is true. So if A is false and B is false, neither of them are true, so the expression is false. If A is true and B is true, the expression is true. If A is true and B is false, the expression is true. If B is true and A is false, the expression is true. I know that can be very confusing. We will show some examples of that in code, so I'm going to forego talking about it more. There's also a critical expression in procedural programming called an if statement. So basically the way you do it is you say if, and you give your little parentheses, and then you put your expression in there. And basically, if says, if this is true, do something. And we'll talk about that. It's called control flow. And then I don't have it listed here because I don't think I wrote these notes out, but there's two other things in the procedural programming world, for loops and while loops. We'll talk about those in actual code. I'm not going to go over functional or object-oriented yet, but I'll briefly talk about them at a high level. Functions are basically ways to symbolically build reusable procedural programming. And then object-oriented combines variables, your data, and your functions into this thing called a class and lets you use it all together. And so maybe it is worth talking about functional. Object-oriented is a whole beast, and we only have 9 minutes, but I think it's very simple. So the way it is written is you write the name of the function. The parameters, those are called parameters, go inside the parentheses. A and B are symbolic parameters. And then if I say C equals A plus B and then return C, C is the thing that gets spit out of the function. So if I were to say B equals add 1, 2, 1, A would be assigned 1, B would be assigned 2, and then C would be evaluated 1 plus 2 and would return 3, and then it would return 3 in the expression, and that this would evaluate to 3, and then D would assign itself to 3, and you would print D, and it would get 3. Any questions on procedural programming?
Good here, Ron. Thanks.
Cool. Have you guys seen this before? I know, Justin, you probably have, but like Rachel and, Jason, you probably have. Rachel and Justin, have you seen that before in like grad or undergrad school or grad school or something?
Yeah.
Okay, cool.
Sure,
So,
I have, but don't remember.
okay. So
I've done
this
quite a
is
bit of
the Python.
scripting, but I'm really interested in how it becomes object-oriented because I can never wrap my head around object-oriented.
Cool. Yeah, it takes a little bit. Fortunately, I've taught this to many people, so happy to explain every intimate detail as we move forward with these lessons. So, so Python, this is just a python.test file. I named it that. My computer knows that it's a Python file, so I put that icon in it. The application I'm in is called Visual Studio Code. And if you guys want to actually program next week in this lesson, I would get Ben or Denzel to install it for you if you don't have it. And then also install Python. And I can give you some instructions on that. You'll want Ben or Denzel to install it because I don't want to have to configure your Docker containers for you. This is not in a container, but you only have admin rights in your container. That's why I said that. They'd have to install Python and Visual Studio Code if you don't have it. But basic procedural programming. So I'm going to write a script. Scripts always are evaluated from the top to the bottom in order. Now, if something along the line calls something that is in the middle, it will like kind of go all the way down and then it will go up to that line. Then it'll go down. We'll talk about that. I have the command line here through Visual Studio Code. It's all kind of integrated for me. And I have the application Python installed. So I can run a Python script by saying Python, the command. The computer knows where the Python application is, the binary. And it will say, okay, I'm going to expect a Python script. So I say test.py because I'm in the desktop right here, test.py. And then I click enter. Oh, geez. Come on. Am I in the desktop? Okay. So I don't have my environment variables set up, meaning I don't have this pointed directly at Python. So I'm just going to use this full path. So full path to Python 3 and then test.py gives me it worked. I didn't get an error, so it worked. I just don't have any code in here. In Python, hashtags are comments. So they don't run. The interpreter ignores them completely. So I'm going to say A equals B. I'm going to assign A1. I'm going to assign B equals 2. And then I'm going to assign C equals A plus B. And then I'm going to print C. Just like that. Python's very easy. It knows the types automatically. You don't have to type them in. And then you run it, and it printed 3 to the terminal. So congrats, we just did a procedural programming. Now I can print anything I want. I can print C, and if I want to add an expression to it, I can add some other string that's like my first code, like that. The plus symbol concatenates or adds like basically the thing that's going to be printed together. I added a space because there's no space if I don't. And then my first code is just a string type. And the way that you do a string type is with, bunny ears or a semicolon or what do you call those? I don't know what you call those.
Quotation marks.
Quotation marks. Why am I like blanking on my
Friday brain? I had it this morning.
basic-
Yes, geez.
I was going to say apostrophes, so
oh shoot! I have to do this thing. There's some nuances, but yeah. So this is a function that converts that number into a string. Print automatically converts it into a string. If it doesn't, it was trying to add a string to a number and gave me an error at first. But if you use this function around string, the C, then it turns into a string, and I can add a string to a string, and then I get 3, my first code. So there's lots of little nuances here that you can do. What we're going to do, what do we got now? We got 3 minutes. Let's do an if statement real quick. So if, just like this, A is greater than B, we want to print, again, it only runs it if A is greater than B. We want to print A is greater than B. Okay, what do we think is going to happen here? What will it print?
Nada.
Should print nada. And it printed, hold on. Nice, I didn't save it. There we go. Test.py if A is greater. Oh, yeah. So it doesn't print anything. Perfect. Now, if we do the reverse and we say B is greater than A, it should print our statement, which is semantically wrong, but it still works. So it runs the expression. If this expression is true, it runs this thing. We could do more fancy things down here, like say C equals 25, or let's say D equals 25, E equals 48, return D minus E. Yeah, the parentheses there, but let's just do this. Let's do F equals A minus B. Return F. Oh, that's not a return. Sorry, that's not a function. This is just an if statement. Let's do print D minus E. So you can do all kinds of expressions inside of your if statement. If statements have all these other complexities like else statements, etc. We'll go over all those over the next software lessons, but this is an introduction to basic procedural programming.